Hello and welcome back. My name is Dr. Mark Taylor. This is the last part of Delaware Tech Physics 111 Lesson 6. Lesson 6 is the third lesson of Unit 2 on forces and energy, and it's a continuation of the section on forces Part 3, which includes work and power. And where we left off was the very last practice problem. This is a work problem that's considered advanced because there is a force that is acting at an angle in this problem, and that requires some trigonometry. All right, so let's look at the problem. Number 7, a person pulls a 50-kilogram crate. All right, let's draw our crate. We'll give it a mass M. Along 40 meters along a horizontal surface. So we've got our horizontal surface, and we're going to pull it along this horizontal surface for 40 meters. It's pulled by a constant force of 100 newtons at an angle of 37 degrees above the horizontal. You can say above the horizontal or above the horizon. So that means we have a force acting on this mass that is at an angle. It's somewhat upward and somewhat across at the same time. And the angle it's forming with the ground is 37 degrees. There is also a frictional force, a 50 Newton frictional force that acts on the crate as it slides. Well, it's going to be sliding to the right, so we know frictional forces always are in the direction opposite movement. So if the movement is this direction, we know the frictional force is to the left. Now, these are the only two forces mentioned in the problem, but of course, there are other forces, and how do we know that? Well, we know it has mass, and it's on Earth, presumably, so it's going to also have a weight force straight down. So we have a weight force, and we know how to calculate weight force. That's just m times g. And there's a normal force because it's sitting on the ground. There's going to be some support force. And you might ask yourself, okay, is the support force the same size as the weight force, like I usually have in problems? Well, in this case, it is not, because these are not the only vertical forces. And you might say, well, where's the other vertical force? Well, you have to remember, anytime you have a diagonal force, you have to break that up into two component forces, a horizontal component and a vertical component. So we have an applied force at an angle, but that applied force, we're not going to actually use that in the calculations. We're going to use the y component of that applied force when looking at vertical forces, and we're going to look at the horizontal component of the applied force when looking at the horizontal forces. So now, if you look at this, you'll notice there are a total of 3 vertical forces: the weight force, the normal force, and the vertical component, the y component of that diagonal applied force. And among the horizontal forces, you have 2. You have the friction that you were told about in the problem, but you also have the forward pointing applied force in the horizontal direction, the horizontal component of the applied force, this value down here. So the movement is in the horizontal direction, specifically to the right, but any horizontal force or force component has to be considered when you're looking at how much work is done in a situation. So part B says determine the network on the crate. Well, the network means you have to figure out the sum of the forces. Well, if we add up the sum of the vertical forces, that's the same thing as the net force in the vertical direction, the y. Well, that's equal to our weight force, which we know is pointing down, our normal force, which we know is pointing up, and our vertical component of our applied force, which we know is also pointing up. And we know that this crate is not magically crashing toward the center of the earth or floating up to the sky. So we know that the vertical forces add up to 0. And in fact, because these are vertical forces, these are perpendicular to the direction that the crate is moving, and therefore they cannot contribute any force to the work. So we don't even have to worry about these forces. But we do have to consider all the horizontal forces. The horizontal forces are the frictional force. Well, let me write. So we have force, horizontal forces, the sum of the horizontal forces, the net force in the horizontal direction, is equal to the applied force in the horizontal direction, which is in the positive direction, plus the frictional force, which is in the negative direction. And do we know that these are equal to 0? Well, they are probably not equal to 0, but we have ways of calculating it. So we can calculate both the applied force in the x direction, and we are given the frictional force. So let's actually calculate these. This sum will equal the applied force in the x direction, and that's the same as the original applied force times the cosine of theta, the angle which we know is 37 degrees. And then the frictional force, we know that value is 50 newtons in the negative direction. So we'll remind ourselves this is going to be a negative force. We'll remind ourselves this is going to be a positive force. Terrible positives there. Okay, so let's actually calculate it. The applied force, 100 newtons, times cosine of 37 degrees minus the 50 newtons for the frictional force. What does that equal? Well, when we plug the 37 degrees, take the cosine and multiply it by 100 newtons, we get positive 79.864 newtons. And then we subtract the friction force, which is essentially fighting against it, and we get positive 29.864 newtons. This is our net force. And now, if you want to calculate the work, at this point, calculating the work is easy. It's just the force in the correct direction, which is in fact the x direction, times the displacement in the x direction. That's positive 29.864 newtons of force times our 40 meters of displacement. We multiply this out and we get 1,195 joules. And if you want to be particular about it, that's a positive value because work is being done on the crate. And this completes lesson 6.